Hello, everybody. My name is Noah Singer, and I'm going to be presenting our work entitled Every Ordering Constraint Satisfaction Problem is Approximation Resistant in the Streaming Setting. And this is joint work with my two collaborators, Madhu Sudan and Santhoshini Velusamy. So in this work, we consider a class of problems called Maximum Ordering Constraint Satisfaction Problems, or MAX OCSPs. And I'm going to define what these problems are in the next couple slides. In this work, ultimately, we give optimal streaming approximation resistance results for every problem in this class of problems. So in particular, we show that for all of these problems, no sublinear space streaming algorithm can get any non-trivial constant approximation. So I'm going to actually start by defining the maximum acyclic subgraph problem, and then describing how max OCSPs generalize the definition of MAS. So in the MAS problem, an instance, which we denote psi, is a directed graph on the first n natural numbers. And the goal of an algorithm is to calculate what we call the value of psi, which is the largest fraction of edges which go forwards over all possible ways to order the vertices of the graph psi. So for instance, here is a graph psi, and its vertices are enumerated in a certain order. And this is not a particularly good order because there are 9 edges, and 4 of these edges actually go backwards, the 4 red edges. But we could permute the vertices of this graph and get a new ordering such that with respect to this ordering, all the edges go forwards. So this is an ordering which witnesses the fact that this graph has MAS value equal to 1. We view MAS as a particular type of problem called an ordering constraint satisfaction problems. So we think of an edge as a constraint which says something about the order of 2 particular vertices or variables in the graph. And instead of saying that an edge goes forward in a particular ordering, we think of a constraint being satisfied by a particular ordering. So in particular, a constraint u comma v will be satisfied by an ordering sigma of the vertices if and only if sigma of u is less than sigma v. And now the MAS value of an instance psi is the highest fraction of MAS constraints which are satisfied by any ordering of the graph. So max OCSPs are a class of problems which generalize the MAS problem. The solution space for all of these problems is still simply the set of all permutations on the first n natural numbers. However, now we can have k-ary constraints which say something about the order of k distinct positions in a potential solution sigma. So given a constraint j, which will be a list of k indices, and a potential solution sigma, which is a permutation of the first n natural numbers, we define sigma restricted to the indices j simply by sigma of j1 through sigma of jk. So we think of a constraint j as saying something about the order of sigma restricted to j for a potential solution sigma. And in particular, it says that it has to satisfy a property which we call a constraint function that we denote by pi. So for instance, for the max acyclic subgraph problem, k equals 2, and the MAS constraint says that if for 2 particular vertices u comma v, that they have to have the ordering 1, 2, and not 2, 1. Okay, so formally, we think of max OCSP as being parameterized by a constraint function pi. And an instance will simply be a set or list of constraints. And the goal is to calculate the maximum fraction of constraints which can be satisfied by any ordering. So we can define the value of an ordering sigma in the instance psi, and then we can define the value of psi simply as the maximum value of every possible ordering sigma for that instance psi. Okay, so another example of a problem which fits the max OCSP framework is called the maximum betweenness problem. So in this case, it's a 3-ary OCSP. The support of the function pi is the 2 permutations, 1, 2, 3, and 3, 2, 1. So in other words, a ordering sigma will satisfy a constraint UVW if and only if sigma of v is in between sigma of w and sigma of u. In this work, we consider the approximability of max OCSPs. So we call an algorithm A an alpha approximation to max OCSP pi problem if for every instance psi, A on input psi outputs an estimate which is in between the value of psi and alpha times the value of psi. And then the crucial question is how good of an approximation can we get to a max OCSP problem with an efficient algorithm? So there's one more sort of piece of background. So for a particular constraint function pi, let rho of pi, and sometimes we'll just omit this pi in parentheses when it's clear from context, be the probability that a random ordering on k variables satisfies the constraint function pi. So for instance, for MAS, there are 2 orderings, and one of them will satisfy every constraint, so rho equals 1/2. So we claim that for every instant psi of max OCSP pi, the value of psi is at least rho. And this just holds by the probabilistic method. Consider a random ordering. Any particular constraint will be satisfied with probability rho, and then use linearity of expectation. So what this means is that for every constraint function pi, the max OCSP pi problem, there's a trivial rho approximation to that problem. So the question is, can a max OCSP pi problem be rho plus epsilon approximated by an efficient algorithm for any constant epsilon? And the terminology for this property, if it were the case that it couldn't be approximated, rho plus epsilon approximated for any constant epsilon, would be approximation resistance. So equivalently, to establish approximation resistance, we have to show that for every very small constant epsilon, efficient algorithms can't solve the promise problem, where yes instances are almost perfectly satisfiable instances of value at least 1 minus epsilon, and no instances are barely non-trivially satisfiable instances whose value is at most rho plus epsilon. We do know, due to this work of Velusamy, Hostad, Manokaran, Raghavendra, and Charkar, that for every constraint function pi, it's hard to get a rho plus epsilon approximation in polynomial time, assuming that the unique games conjecture holds. But without the unique games conjecture, the previous results are the best that we know how to do. Okay, so in this work, we actually consider not in the full setting of polynomial time algorithms. Instead, we consider approximability in the setting of so-called streaming algorithms. They only get polylogarithmic space, polylogarithmic in the number of variables in the instance, and they only get one pass to the list of constraints in the instance. So they sort of see all these constraints coming at them in a giant stream, and they don't have very much space to remember them. And the reason why this is an interesting model is because we actually know how to prove unconditional lower bounds for approximations for many interesting CSPs, typically by reducing to communication problems. So what was previously known about the streaming approximability of max OCSPs in particular? So as far as we know, there were no inapproximability bounds for max OCSP pi for any constraint function pi aside from MAS. And for MAS, there was a paper actually in Approx 4 years ago, which showed that you couldn't get 7/8 plus epsilon approximations in sub square root n space. And this proof was by a gadget reduction to the from the Boolean hidden matching problem. And then later there was a second Approx paper which improved the 7/8 to a 3/4, and this time via a streaming reduction from the unique games problem. But this 3/4 is still not optimal, because optimal would be rho equals 1/2, and also the space bound isn't optimal. It's only sub square root n space. Okay, so in this paper, we show that for every constraint function pi, the max OCSP pi problem is streaming approximation resistant to sublinear space algorithms. So more formally, what this means is that the promise problem of distinguishing almost perfectly satisfiable and barely non-trivially satisfiable instances can't be solved by sublinear space algorithms, where n is, again, the number of variables in the instance. And by the way, this space bound is actually optimal due to, at least in the way that we define the model. So we define the model as only having space restrictions and not time restrictions. So once you get a linear space, what you can actually do is sample a linearly large subinstance psi and then solve of the input instance, and then solve exactly, say, in exponential time to get its max OCSP value. And then you can use concentration bounds to show that since this is such a large subinstance, that its value is close to the value of the original instance with high probability. Okay, so what are the actual ingredients which are used in our proof? So we define a pair of distributions, which we call the yes distribution, gy, and the no distribution, gn, which are indistinguishable to sublinear space streaming algorithms, such that with high probability over yes instances, the value is high, and with high probability over no instances, the value is low. And then we combine three different sort of results or techniques in order to conclude the streaming inapproximability. So firstly, we use the streaming inapproximability results for sublinear space algorithms, which were recently proven for various non-ordering CSP problems. And I'm going to define more carefully what a non-ordering CSP is in the next couple slides. Secondly, we use a notion called coarsening which essentially is a way to convert from an ordering CSP to a non-ordering CSP. And this idea was essentially the same as the coarsening idea, which was used in this Velusamy et al. Work, which proved unique games hardness in the classical setting. Finally, we conduct a combinatorial analysis of certain small set expansion properties of instances which are drawn from the no distribution. And this sort of allows us to translate these hardness results through this coarsening notion to work for ordering CSPs. I'm going to sketch sort of how the proof works for the particular special case of the maximum acyclic subgraph problem. And everything will generalize suitably. Okay, so first I'm going to define what a non-ordering CSP is. So in these problems, they're specified by a constraint function f, and the solution space is going to be assigning every variable of the n variables a value in a finite alphabet of size q. And so now the constraint function f will look at the different assignments of k variables, each assigned from this alphabet of size q, and say whether that's a valid assignment or not. So we can again define the value of an assignment b, and then the value of an instance psi as the maximum over all possible assignments b. Notationally, we put an overline over the values of a non-ordering CSP instance, just to make it clear that that's a non-ordering CSP and not an ordering CSP. Okay, so the idea behind the proof is to translate hardness results, and in particular, we're going to use this recent hardness result due to Cho, Golovnov, Sudan, Velusamy, and Velenker, and these results were proven for non-ordering CSPs, and we're going to translate them to the setting of MAS. And the way this proof is going to work is we'll choose a large finite alphabet size q and a binary constraint function f, such that we'll get from this Cho et al. Work that the max CSP f problem is hard to approximate in the streaming setting. And then what we're going to do is, given any list psi of two array constraints, we'll view it simultaneously as an instance of the MAS problem and as an instance of the max CSP f problem. And note, by the way, that I haven't actually specified what this function f is. I'm going to first say what the properties that we want to hold about it are, and then I'm going to define it later. But we can view any instance psi of MAS as a max CSP f instance and vice versa. Okay, so our plan is to select these gy and gn distributions to be the hard distributions for the max CSP f problem from this Cho et al. Paper. And then we're going to use the properties of f and gy and gn to relate the value of an instance psi as a max CSP instance and its value as an MAS instance. And this relationship will let us conclude that these distributions gy and gn are also hard distributions for MAS. Okay, so since we picked gy and gn to be hard instances for the max CSP f problem, what do we know? So we know firstly that they're going to be indistinguishable to sublinear space streaming algorithms. We know that gy will have high max CSP f values with high probability, and then gn will have low max CSP f values with high probability. Okay, so next we're going to construct f in such a way that we can conclude that for every instance psi, we have that its MAS value is at least its max CSP f value. And finally, we're going to do a particular small set expansion analysis of the distribution of no instances gn. That's going to show that with high probability over a no instance psi, its MAS value is not too much larger than its max CSP f value. And so why are all of these results together sufficient to prove the theorem? So note that 2 and 4 together imply that with high probability over a yes instance, its MAS value is at least 1 minus epsilon, whereas 3 and 5 together imply that with high probability over a no instance, its value is at most 1/2 plus epsilon. So now I'm going to actually tell you how we define this f function in order to make these properties on the previous slide hold. So we're going to pick f, and remember this q, the alphabet size is large, to take two inputs u and v and simply be the indicator for u being less than v. And the sort of high-level intuition for why this might make sense as a choice is that we can essentially view MAS as a non-ordering CSP of this form, except that the alphabet size is now n instead of q. So our entire result can sort of be viewed as an alphabet size reduction from a linearly sized alphabet to a constant size alphabet for a sufficiently large constant. So our first claim is that if we define f in this way, we have property 3 from the previous slide. To be specific, so for every instance psi, its MAS value is at least its max CSP f value. So why is this the case? So I'm going to do a proof by picture. So given an assignment B to the max CSP problem, I'm going to construct an ordering psi, which is an assignment to the MAS problem, such that the value of psi is at least the value of B. Okay, so I start with this instance psi, and here I've labeled psi's variables as A through I, just so that we don't have too many numbers floating around. And there's an assignment B, which assigns to each variable a value in an alphabet of size q equals 4. And B's value is 2/3, because for instance, if we look at this constraint that goes from A to B, this constraint is not satisfied because A's assignment is 2 and B's assignment is also 2, and 2 is not less than 2. Okay, so how am I going to construct this ordering sigma? What I'm going to do is I'm just going to place all of the vertices with slash variables with label 1 first, and then label 2, and then label 3, and so on. So I put some of the variables with label 1, then some of the variables with label 2, then some of the variables with label 3, and this made my ordering sigma. And now the question is, why is sigma's value at least as high as B's value? So the point is that every constraint that's satisfied in the max CSP version will still be satisfied in the MAS version. And we may actually gain. So for instance, if we look at this constraint that goes from A to B, originally in the max CSP setting, this constraint was not satisfied because 2 is not less than 2. But now in the setting of sigma, of the ordering sigma and MAS, this constraint will be satisfied because A comes before B in the ordering sigma. So this constraint was previously bad for us, but is now good for us. And in fact, the value of this ordering sigma in the MAS instance is 5/6. Okay, so this suffices to prove property 3. Okay, now going to talk a little bit about why this choice of F gives us approximation resistance results for the max CSP F problem in sublinear space from this Cho et al. Work. Essentially, it follows from a particular property of F called the width of its support. So what this means is that if we look at all of the pairs like F1, 2, F2, 3, F3, 4, etc., almost all of them will equal 1, except for one particular value of f of q comma 1 will equal 0, because q is not less than 1. But for every w which is not equal to q, f of w, w plus 1 will be 1, because w will be less than w plus 1. And this property is called width, and this Cho et al. Paper says that if you have a wide constraint function that you start with, then the max CSP problem will be hard to approximate in sublinear space in the streaming setting. But all of this together, we still are missing one property, which was property, actually this should be property 5 from the previous several slides ago, which says that with high probability over a no instance, its value as an MAS instance is not too much larger than its value as a max CSP instance. Okay, so GN is essentially a type of random graph, and this definition of GN comes from the Cho et al. Paper, which is why these things are on the same slide. So GN is essentially a random graph, but it's this weird random graph model where we randomly subsample edges from a union of random partial matchings. But it's sort of like it's a type of random graph, but it's a little bit of an unconventional random graph. Finally, how do we get this property 5 that we wanted in order to conclude the proof? So given an assignment sigma to the MAS instance, we want to create an assignment B to the max CSP instance, so that the value of sigma is not too much larger than the value of B. So how are we going to do this? So we're going to start again with a picture. So this is the same picture as from a few slides ago. And the way we're going to construct B is simply by assigning the first several variables the value 1, the second several variables the value 2, etc. And then we're just going to hope that this doesn't make too many edges that were good for us, bad for us. So in particular, note that in this picture, the edge from A to B was good for sigma, but is now going to be bad for B, since 2 is not less than 2. However, as long as we have a certain property, which we call small partition expansion, which says that given any partition into small blocks, not too many edges will go from a vertex in a block to a vertex in that same block. As long as we have a property like this, it essentially implies that from going from sigma to B, we're not going to lose too many edges. So the value of B won't be that much lower than the value of sigma. Thank you.